Bridge rectifiers are the modern way of creating what's called full wave rectifiers. In essence, they have 4 tiny silicon diodes inside them, and this is what the output from them looks like on an oscilloscope.
Well, this is a bridge rectifier. It's just nothing to look at all. It's a little black blob of hard plastic with 4 wires coming out of the bottom. And if you can see those wires in this image, 2 of the wires are connected to the AC part of the circuit, and the other 2 wires are connected to the DC part of the circuit. One wire is positive, the other is negative. And although you can't see it, written on the top of the bridge rectifier are some numbers designating what type of rectifier it is in terms of how much current it can take and voltage, and also designating what each of the little wires is in terms of either AC or DC. But that's all a bridge rectifier is to look at. Of course, they come in bigger and smaller sizes than this, but that in essence is a bridge rectifier. So things to note then about this full wave rectifier, and one is that it looks actually very much like an alternating current insofar as it goes up and down and up and down, but it's not. It's all direct current. It's all travelling in one direction. And you might notice that, although it's flashing around a little bit here, instead of 50 Hertz, instead of seeing 50 peaks every second, we're now seeing twice as many. And that's because the negative half cycle of the alternating current that would have been going in that direction is now being converted to work and go in that direction. So we're seeing twice as many peaks as we did with the half-wave rectifier, which, if you remember, had long periods where no voltage was flowing between the peaks at all. So now it's all direct current and it's all going in the same direction. So here we have then a bridge rectifier, which in turn creates a full wave rectifier. Down here is the secondary, sometimes called the output winding from the transformer. And we know that the alternating current across this output varies. Sometimes the top is positive, 50th of a second later the bottom is positive. And then the top becomes positive and the bottom incidentally is negative. And then a 50th of a second later it reverses again. So how can we understand what's actually happening in this circuit? Well, one way is to analyse what happens moment by moment. So in this instance, let's imagine then that the top of the output winding, the secondary winding, is positive and the lower part is negative. Now the current, the electric current, wants to get from positive to negative. In conventional current flow, the electricity flows from positive to negative. It wants to get to negative from positive. So let's see what options are available to it. It starts by coming down here and then it finds a fork in the road, so to speak. Now it can't come down this way because this diode is offering a very high resistance. The current through a diode is only allowed to flow in the direction of the arrow of that diode. So the current can't come down here. Instead it has to take a route up here. So it takes that route. Oops. It can pass through this diode because the current is flowing in the direction of the arrowhead and come up to this point. So I'm just going to colour this diode green. Green for go. This diode becomes forward biased and turns on. Then the current comes up to this point here, and again it has a choice. It can either try and come down here, but once again this diode is shut off. it's not going to allow the electricity to flow through it. It's offering a high resistance. So in which case the electricity has to turn along this top section here. Comes along, does a sharp right-hander, comes down to the light bulb, illuminates the light bulb as it goes through it, gets to the bottom of the circuit here, does a quick handbrake turn in that direction, comes along, jumps over this vertical wire and gets to this point back at the bridge rectifier. Now let's remind ourselves, the current wants to get back to here. So it doesn't want to pass up this route here because it won't get to the negative terminal here. So the only place it can go is here through this diode and then back to the negative side of the secondary winding. Let's colour this diode in green as well then. Ta-da! So, when the top part of the secondary winding is positive and the lower part is negative, these two diodes will be in operation to allow the current to flow through the circuits and get back. Well, nothing too complicated there. But what happens when the bottom of the secondary winding is positive and the top is negative? Let's have a look. Okay, so now we're going to assume that the lower part of the secondary winding is negative and the top part, the lower part is positive and the top part is negative. So the current wants to travel in this direction. So it comes along, it does a quick right-hander, and it comes up to this point here. Now the current can't flow this way because this diode will be offering a high resistance. It only allows the current to flow in the direction of the arrow. So in that case the current has to flow up to this diode here, turning this diode on. The current will forward bias this diode. We'll colour him blue just to be different. When the current gets to here, he can't go down this diode because the current flow won't allow it. So he does a very sharp right turn. Oops, if I can get the pen to write, that would be useful. We're pretending these arrows are showing the direction of the current. And he goes along here, down through the bulb, round the corner, and hops over the vertical wire and gets to this point. Now, if we remember, he wants to get to here, to the negative part of the secondary coil. So the only path available is this one, this diode here. So we'll colour this diode in blue as well. There we are. And lo and behold, then the current passes through this diode and gets back to where it wants to be, negative. So when the lower part of the secondary winding is positive and the top part is negative, these two diodes are in operation. When the top of the secondary winding is positive and the lower part is negative, these two diodes are in operation. But no matter which way round the output winding of the coil of the transformer is, no matter which way round they're polarised, the current always flows in this direction in this part of the circuit and in this direction in this part of the circuit. So we have AC here being converted into DC up here. It's just that when the positive and negative aspects of the secondary winding are in one configuration, these two diodes are operating and when the positive and negative aspects of the secondary winding are in this configuration, these two diodes are in operation. There's just a couple more things for me to tell you, and that is that each of the two diodes, whichever two they be, require 0.6 to 0.7 of a volt to turn on, and they reduce the overall voltage in the DC circuit by that amount. Given that there are always at least two diodes turned on, then the total voltage drop, the total reduced voltage available in the DC part of the circuit, will be between sort of 1.2 and 1.4 volts, and that reduction can be significant in some low circuit DC requirements, so it has to be borne in mind. So we now have all the current going in the same direction, it's all DC, and although there are far fewer periods of time where no voltage is flowing, there are some periods of time where no voltage is flowing, right on the bottom here. But if we take our friendly capacitor now and place that in parallel with the load, we can see that there is absolutely no time at all that 0 volts are going to the bulb, and in addition to that, the ripple current on the top is much less pronounced now. The difference between the peaks and the troughs is barely noticeable, so a lot more current is getting to the load, light bulb in this case. Take the capacitor out of circuit, and there are brief periods of time between each of the peaks where there is no current, no voltage reaching the bulb. With the capacitor in circuit, however, that ripple current, as it would be, is greatly reduced, and we have virtually as much current going as we would do if we were using a battery. Full wave rectification with a smoothing capacitor. So here's a circuit diagram, commercially produced or commercially printed circuit diagram, rather better than my scribble. What's going on over here we won't bother about. This is a regulator. Maybe I'll do a regulator, how regulators work a little bit in another video. But from here on to the left, we can see this is the transformer, slightly different schematic to that you've been used to seeing, but 230 volts in, 13 volts AC coming out. Here's the bridge rectifier with its 4 internal diodes, and here's the smoothing, or what I used to call reservoir capacitor, to even out that ripple voltage that we spoke of before. And this is exactly what you've just been learning. Incidentally, you might realize that you're now reading circuit diagrams. Wonder whether you realized you'd be doing that when you started out on your interest in amateur radio. Anyway, that's it for now. Bye.